So today it's my great pleasure to introduce Sanjay Behura, who's the brand newest member of the physics department. And walking over here, I assured him that the entire audience would be really up to speed on condensed matter physics. So I want to make sure I let you know I promised that of all of you. So Sanjay is a condensed matter physicist. He specializes in the photophysics of quantum materials and explain to you what that means. His areas of research include large-scale growth, structure property characterization, and light matter interactions in thin quantum 2D materials and engineered heterostructures. So he presently is studying quantum light emission phenomena in van der Waals materials for quantum information science technology, which is all the rage. Wants money in it. He is also investigating the physics of quantum materials for development of green energy technologies, is developing next generation photovoltaics, such as dye-sensitized solar cells for organic solar cells and 2D material-based heterogeneous solar cells, which I think you mean I'm okay that I put off putting solar on my roof so far. For your years of saying. Without further ado.
Good afternoon, everyone. Thank you so much, Alvin, for this nice introduction. Thank you for invitation. It is a great pleasure to be here and talk about my research program, which is about quantum materials in general and photophysics in quantum materials in special. So you can see here, the topic is photophysics in quantum flatland. So what I mean is the materials that I'm going to discuss today are all flat. They're just one atom thin, or just one atom thin and spread in X and Y directions. And we'll see how we can get different properties out of these materials by one on another, by twisting one material on top of another, and we'll see how new physics can emerge and we can design new structures as well as new devices. So before I move, okay, I should thank all my collaborators and students that worked on it and all the sponsors. So recently we have received the funding, and some of the funding I'm trying to transfer here that will have new PhD students working in the topic that I'm going to briefly discuss today. So broadly, this is what my group will do. So we are going to design, create these quantum materials in a large scale. Okay, so we were having a quantum materials growth lab where we are going to create these materials. This is a hexagonal boron nitride that I'm going to discuss how we are going to see different atomic or molecular defects, and we'll see how light, quantum light, it's not classical light what you see, the quantum light can be emitted in those materials. And we'll also see that if I can take two layers of boron nitride, the boron nitride material, and I twist at certain angle, and you see the Moire patterns, and from each Moire pattern, we can also have solid state quantum light source that will be eventually used for photophysics analysis, and finally having applications in quantum information science and renewable energy. Okay, so then what are quantum materials in general? Okay, so materials which are very small and having property that you can see here. You have low dimensional carbon materials for an example here. And you can see here they have interesting properties because of the quantum confinement. As soon as you have a material in the 2 dimensions, electrons are confined in 2 dimensions. That means they can only travel here in X and Y. There is no movement in the direction. So that confines their transport, and that leads to interesting energy band gap in these materials. Similarly, if you confine or if you confine the electron in 1 dimension, then it's a 1-dimensional wire, just like carbon nanotubes. You can also confine the material from 3 dimensions, and you will get a ball-like structure of quantum dot, something like a buckyball. And not only the electronic confinement, we can also, as soon as we reduce the dimensions, as you can see here, an example, a 6 meter square cube, if we further reduce the dimensions and divide into several blocks, you can see we can increase the surface area. So more the surface area, more reactivity they have, and accordingly, they can be useful for various applications. So this is graphene. As you can see, graphene is the building block for all the carbon materials. It's a two-dimensional material, just one atom thing. You can see here, and it has only 2 carbon atoms per unit cell. If you see the unit cell of this graphene, even though it can look like there are 6 carbon atoms in a honeycomb structure, but there are only 2 atoms per unit cell because other atoms are actually shared in different honeycomb structures. So that leads to interesting electrical properties because of the 2 atoms in the unit cell that occupies all the valency band, and conduction band is completely free, and they touch each other here. And in order to explain the physics of graphene, we cannot just use the Schrodinger equation that we can use in other semiconductors. We have to use the Dirac equation. So in order to explain the physics of electron transport in such a structure, and you probably don't find a material just like graphene where you will have a 0 band gap. Okay, so you see here the conduction band and the valence band, they touch at the Dirac point, and it has a 0 band gap. So another interesting property is the optical property. Here you can see when the graphene is just a single layer, so it is very transparent. As soon as you add another layer, then the transparency decreases by 2.3%, and this is because of the fine structure constant, which is very close to the point of electrodynamic behavior of the graphene. It is considered the building block, so that means we can stack them and form graphite that we use in batteries. We can roll them from carbon nanotubes, and depending on how we are rolling and how the edges are connected, so we can have conducting or semiconducting or insulating carbon nanotubes. We can wrap them into buckyballs. So graphene is not the only material that we are interested. There are varieties of materials that our group already synthesizing and going to synthesize here. One such material is hexagonal boron nitride. You see here graphene I showed the 0 band gap material. As soon as you replace carbon by alternating boron and nitrogen atoms, you have a wide band gap. Just the same material, but you replace carbon by boron and nitrogen, you have Waals thickness insulator. You don't get any material having this energy band gap. So, and then as far as electronics is concerned, this is not good because it's an insulator. So then we have other materials, band gap between 0 to 6 electron volts. So which are transition metal dichalcogenides, such as molybdenum disulfide, tungsten disulfide, and other selenide and telluride based materials. Then we also have other phosphorus structures like black phosphorus, where the band gap can be tuned from 0.3 to 2 electron volts. And there are a wide range of optical energy that you can see here, starting from ultraviolet because of the large band gap to microwaves and radio waves. So the whole spectrum of the electromagnetic light can be observed if we can take individual materials and stack them, as you can see, so we can observe the entire electromagnetic spectrum. So now how we can use them to apply in various applications. So not the individual material, as I said, we can also stack them, okay? Because you can see here graphene, boron nitride, different transition metal dichalcogenides. They're actually just like Lego blocks because they're atomically thin and you do not need a lattice mismatching to stack them. So you can stack them and just like we create our chassis. Okay, so not only stacking them, we can also stack one material, graphene, on another graphene, and it twists at a certain angle. Okay, let's say you twist to just 1 degree or 2 degree, the top graphene versus the bottom, then you suddenly see a superconductivity there in graphene. Okay, so it is called, physicists hide this, and this is called twistronics, just like spintronics, or other electronics that you can see. This field just recently become so popular, and it has a name called the twistronics. Okay, so you twist it and you see different properties, and you can twist from 0.01 degree to up to 60 or 180 degrees. So we'll see how we design these materials and also use them for quantum and renewable energy. So one of the most important challenges now is that atomically thin, very sensitive, right? Just one atom thin material, and how we can synthesize them precisely over the large scale. So you can use, just like any nanotechnology approach, you can use 4 different approaches. Actually, top-down, the 2 top-down approaches, 2 bottom-up approach. So you can actually use exfoliation strategy. So you can take a graphite, piece of graphite, because graphite consists of individual layers of graphene, and you can actually use a small step that we can do in our lab and exfoliate individual layers and from. And this is the technique, Nobel Prize winners actually use it, the simplest technique, and you can get the best quality material out of this. However, this is not useful as far as application is concerned, because you can only get a tiny crystal out of it. And the crystal may be really high quality, but if the size is very small, you can use chemical exfoliation. Chemists, they love to do oxidation or reduction of graphite. You can see here the oxidation, ultrasonic reduction. You can produce milliliters or liters of graphene oxide in a solution form. However, the quality is not very good, because as soon as you oxidize, so there are defects within the structures. So that may not be good for electronics. There are the 2 approaches. One is epitaxial growth on silicon carbide. You can take a silicon carbide crystal, because it consists of silicon and carbon. You can actually boil it and remove silicon from top, and the carbon on top, carbon that is already on the surface, that crystallizes to form graphene. So you have a graphene structure already on silicon carbide, which is an insulator. The approach that we use, and we are going to have a dedicated lab called chemical vapor deposition, where you can actually produce high quality and large area. The limitations that you have in all these approaches can actually overcome in the 4th approach. So let's see how. So we can use CBD to actually grow on different metals. You can see here iron, cobalt, nickel, and copper, because of the catalytic nature of the metal surfaces. Or as soon as you have graphene grown on a nickel surface or cobalt or iron, then what happens actually, the carbon, because we generally use a hydrocarbon source, methane, which breaks down to carbon and hydrogen. And carbon actually at high temperature, it fuses into these metals. And when we cool down, then this carbon comes out and then actually forms graphene. So you can see here that controlling the layer number, for example, I want to grow 1 layer versus many layers, it is difficult now, because you don't know how much carbon going inside. So the second approach is copper. Copper doesn't react with carbon very strongly, because it doesn't form copper carbide. So actually the growth is limited to only to the surface. So you can actually grow a single layer. So if you want a single layer graphene, then you can go for copper. If you want multi-layer graphene, you can go for nickel or any other. So problem, as soon as you have graphene on these metals, irrespective of whether it is copper, nickel, or cobalt, or iron, silver, or gold, any metal, we cannot use it, because you cannot measure electrical conductivity of the material which is sitting on a metal. So we need to transfer on that insulating substrate. And transfer process is complicated. You have to go through all those steps. having a layer, a polymer layer on top, then removing the metal, and then you can see here the polymer holding the 2D material, and then finally transferring on a dielectric. Which in order to avoid all these processes, what our group have already discovered that we can actually grow these materials on insulating substrates directly without using any metals. So that's what the topic today. So I'll tell you how we have designed a new physics, the surface physics, that we can grow all the 2D materials directly on a silicon-based substrates where we do not need to transfer the materials grown on a metal, and we can actually really grow on the large scale, in large scale. And finally, I'll talk about the light matter interactions with this material. So first, I'll talk about graphene, then boron nitride. So here, this is the structure. This is the process how we can grow graphene on a dielectric or an insulating substrate. We started with the silicon substrate that we use, in our integrated circuit. We have a polycrystalline copper. So you can ask why still there is a metal, but we use the polycrystalline copper here. So polycrystalline copper, there are a lot of grain boundaries. That means, it's not a single crystal smooth surface. So since it's polycrystalline, so what happens? You have carbon can diffuse. You can see here the grain boundary is actually connecting from top to bottom. Also, while the grain boundaries can be on the surface only. So the carbon methane which dissociates into carbon and hydrogen can actually diffuse through the grain boundary. So since it can diffuse through the grain boundary, the graphene can form directly here. And you can also ask that, isn't it there is a graphene here at the top? So there will be two graphene there. So one will be here on top as well as at the interface. So we remove the top graphene along with the copper. We have graphene directly on the dielectric substrate that you can see here, continuous graphene there, and we can actually control the growth and understand how they can grow by controlling the number of grain boundaries. So we have the island-like nucleation structure to graphene island to a continuous graphene, and we have grown it in a wafer scale for industry level for wafer scale. And then the material, once it is grown, it is important to understand whether it's a good or bad. That we can actually characterize by building a transistor circuit, the electrical transport measurement at a low temperature of 10 Kelvin. So we have built the graphene here. Then you have metal connected to the edge of the graphene, and then we actually apply voltage and measure the current, and then we calculate the current versus voltage. And the voltage is actually converted to carrier concentration, that how many electrons are there in graphene, and then we can also actually convert the same plot into resistance versus carrier concentration to understand the charge carrier mobility, which actually defines for the electrons and for the holes for the interface. Now let's look at other materials. Next material is boron nitride. As I said, it's very similar to graphene. However, you can see here instead of carbon, you have boron and nitrogen alternating in a honeycomb structure. So because of the boron nitrogen, the symmetry is broken, and they have a charge. Because of the dissimilar charge between boron and nitrogen, there is a large energy band gap here, which causes 0 energy band gap for graphene. You have 6 electron volts of energy band gap. And if we compare boron nitride versus graphite, there is a little offset here in the second layer, and it has a lot of interesting properties. Can be used for the quantum emission. That is one of our applications to dispersion inks, to ferroelectricity, a proton exchange membrane. We can also use boron nitride as the thinnest membrane for proton exchange fuel cell. We can also use, since it's an insulator, and it is the most thinnest insulator, you can actually use it as a tunneling layer in a tunneling transistor, and also use it as a gate dielectric for other 2D materials. Then again, growing these materials is difficult, and again in a large scale. So we have different approaches, top down and bottom up. We can physically exfoliate. However, the quality may be better, but the size is small. So we generally adopt CVD approach. So chemical vapor deposition of boron nitride on silicon substrates as well as sapphire substrates. So this is how we design our chamber. This is a high temperature, low pressure chamber, and we use hydrogen gas. And then here instead of methane as a gaseous source, we use solid source for boron and ammonia, because those are the precursors for boron nitride. And you can see here we have large area boron nitride, continuous boron nitride on various substrates that we have grown. Silicon oxide, a quartz, it's transparent because the one layer is transparent, you cannot see. But a laser can see. You can use a Raman. That is what we would have, a Raman spectrometer in our lab that would be used to actually detect this boron nitride modes of the vibrational modes of the boron and nitrogen atoms. You can see here the E2G band that corresponds to boron nitride, and since it is on a silicon substrate, therefore there is a silicon band here, and this is an optical spectroscopy measurements which actually confirms the energy band gap, which is close to 6 electron volt. 6 electron volt is for one layer, but if you have few layers, then the band gap is actually reduces. Most interestingly, boron nitride is very smooth. So if you look at silicon oxide, which is in our mobile phones, in our laptops, all the integrated circuits are made up of silicon. But we propose to use boron nitride because they are having high thermal conducting, they're smooth, they actually use less power. Okay, so this will be the next generation integrated circuit materials. You can just compare the smoothness of boron nitride layer coated on a silicon oxide versus just silicon oxide measured using atomic force microscope. And then it is also important to understand how we can grow these materials. So as I discussed, we used a solid precursor that actually broken into several other precursors here, which is a Boron, which is mostly just like a benzene kind of structure, and then the polymeric amino boron, which actually transport through the boundary layer and reacts on the substrate, and then we get boron nitride. We also do some molecular dynamic simulations and to understand how different substrates can grow different. Boron nitride on different substrates can grow different. For example, the absorption of these molecules on a silicon nitride surface is actually less versus on a silicon oxide surface, because in the silicon oxide there are a lot of oxygen. So these molecules actually bound to the oxygen in a higher rate versus they can bind on a smooth silicon nitride surface. And then just like graphene, we also actually we have boron nitride here. We place the graphene on top of it and then build the circuit to measure the charge carrier mobility of graphene. You can see here. So this is the charge carrier mobility of graphene when it's on a boron nitride surface versus on a simple other dielectric surface. So we have almost 3 orders of magnitude higher current of graphene when they are sitting on a boron nitride. So what we propose is 2D materials or any other materials. You can use boron nitride as a platform because it's an insulator, it's smooth, it is having high thermal conductivity, and it doesn't actually react with any materials. It's chemically inert. Finally, so we can actually create these heterostructures. As I mentioned in the beginning, we can use them and actually find different properties. We actually created those. We started with silicon oxide. You can grow boron nitride on top, and then use polycrystalline copper and grow graphene on top. And then what we found that that these materials are actually twisted. So they are thermodynamically favorable because of the thermodynamics that so graphene is twisted directly on boron nitride at an angle of about 16 degrees. So these are all twisted structures. So our next goal is to actually control the angle. So we have just 16 degrees where graphene is actually sitting on a boron nitride. We wanted to control the conditions, growth conditions, so that we can actually control all the angles, 1 degree, 2 degree, up to 60 to 180. So each one of those actually is a different quantum material. And you can see here for the 16 degree, this is the electronic transport. Again, we have this twisted structure of graphene and boron nitride, and we can measure the current voltage, current versus voltage, which can be actually a carrier concentration. The voltage is converted into a carrier concentration at about 14 Kelvin, which is close to liquid, not liquid helium, but little higher than helium. And finally, show you how we can actually use these materials, and we study strong light matter interactions. One such structure is putting graphene on a silicon substrate and shining light, and then understanding how charge carriers transport across this junction. We have graphene here, and then you have silicon here. Silicon has a band gap, graphene has no band gap. You can see here it's a kind of a mixed, what we call mixed dimensional structure. You have 2-dimensional versus 3-dimensional. So as soon as the interface, you have this structure, because of the electric field at the interface, the electrons are transported towards silicon side and holes are transported towards the graphene side. Now let us see what happens if we put some metallic nanoparticles on top, or having a 2D material on top, and if we can actually use a boron nitride layer between the interface of graphene and silicon. So we can use metals on top of graphene, even though graphene is chemically not a perfect graphene. However, we can actually use some chemistry to anchor the metal nanoparticles on top. So as soon as we anchor metal nanoparticles, we measure the current and voltage. You can see there is significant increase in the current because these metal nanoparticles have the more light versus graphene. And the chemistry here. So you can see here, this is just graphene, and these are metal nanoparticles coated graphene after the functionalization that is going on here. So the functionalization that doesn't create any defects, that is confirmed from here, that the sp2, the sp2 hybridization, because it's a honeycomb structure, so sp2 hybridization remains as it is after the graphene is functionalized with a chemical. Okay, so and further, the charge carrier mobility, if you functionalize any chemical, the charge carrier mobility actually reduces significantly because of the defect, and most of the time it actually converts to sp3. But you can see here the sp2 net hybridization remains same, the charge carrier mobility remains. So that signifies that this process that helps in protecting the graphene structure. And we can also do same thing, further enhance the current by placing it another 2D material for tungsten disulfide, because it has high absorption coefficient of high absorption for visible light. That we have actually grown this material on graphene, so using sulfur as one of the precursors and tungsten another precursor, because it's a tungsten disulfide. You can use tungsten oxide and sulfur, and you can grow it. And as proposed, it's supposed to increase the current significantly. And the mechanism that drives this, you have two junctions here. First one is graphene and silicon, and with tungsten disulfide on top. There are two junctions. One is tungsten disulfide on graphene, and graphene on silicon. So the effective electric field drives the electrons and holes across the junctions. And finally, since both of the cases you see that there is a chance that we can increase the current, but the voltage still remains low. So one approach is to introduce a thin boron nitride layer, as we have done here, between graphene and silicon. So basically, we're trying to play how different ways we can have strong light matter interactions in these 2D structures. So that actually helped us to increase significantly the voltage. So we have this is the graphene silicon. As soon as we have a interfacial boron nitride, that helps in enhancing the barrier, which restricts backflow of electrons towards graphene side. Electrons are supposed to move towards silicon. As soon as they move backward, that reduces the voltage. So because of the boron nitride interfacial layer, this barrier becomes higher versus just graphene silicon, so the voltage is higher. Just to summarize the three different structures for this 2D material on a 3D material mixed dimension structure. We can have nanoparticles on top. We can use another 2D layer on top of the first 2D layer, and we can introduce a boron nitride layer. Thank you. And then finally, I did not forget that we have one grant is coming, and there will be one PhD position open, where what we are going to do is actually understand light matter interactions in the twisted structures, and we also have computational machine learning and other computational tools to look at the experimental procedures that we are going to do. So it's a both experimental and computational PhD. So this is grant is on the way, and there will be one PhD position in this grant.
What questions?
Curious about this twisting that you do. Does the energy state cause it to be in that twisted configuration already when you lay it down, or do you have to do something to twist those layers? And if so, what is that control that allows you to twist by? So say you can do it by 150 degrees, right? So
How we can do the twisting? So basically, we can do there are two different ways. One is here we can directly grow, okay, and can directly grow the top layer, which is already twisted. You can see here, and I think there is a video here. So you can directly grow. You can see here. So as soon as the twisted structure, see the moire pattern are different, and there actually is a large the prints. The distance between these patterns is larger versus say just one layer. Okay, so we can grow it directly. That is what which not done. So we are trying to grow them in a larger scale. But before growing, we can also lab that we are having one called twist and stack and twist approach. So we can use the graphite. We can peel one layer and transfer on a silicon substrate, and then we have let's say boron nitride crystal. We peel another layer, and then the robotic way of doing so, which will be in our lab in a few weeks. So that will stack on top, and then we have a motorized, just like we have Xbox box that we control the games. We can actually tweak different angles. So this is a completely motorized system inside a globe box. So there will be, so that means as soon as these stacks are placed on top of, there will be no impurities between those stacks. Because you can see that any tiny impurity can also change the whole electronic structure. Therefore, we want to be inside a globe box with control and movement. That answers it.
This is more about the computational machine learning aspects.
Oh, sure. So computational, almost all the projects that actually I have not put computational because experimental are so much. So every project we have computational aspects. So here for the last one, we will what we'll do the twist angle that the twisted structures that we will create at different angles, and then the optical properties that we are going to measure from each of those structures that we'll use as input parameters for machine learning analysis, where we will be able to predict, what will happen at the different conditions at different angles or different laser powers or different temperatures. So this is what we will try to predict. So someone with background in experimental as well as computational approaches will be good, but if no background also will be able to.
You're talking about optical properties. Can you explain a bit more what you're meaning by that? Because these dimensions are too small for spectroscopy to really affect.
So optical properties, when it actually the exciton energy, the exciton energy. Okay, so excitons we know, right? The bound electron hole pair. So generally you see excitons in one layer. Okay, so as soon as we have two layers and we twist them, you can see interlayer excitons. Okay, so you have intralayer excitons, that means electron hole bound pair within one layer, and then there are interlayer. So electron in one layer binds with hole in the second layer. So that forms intralayer exciton. We want to understand the energies of those excitons through optical measurements. Okay, and once we understand those at different angles, and we want to predict what will happen in the much wider angles or lower angles or different temperatures. And then because of those interlayer excitons, we want them recombine and produce a light. That's called quantum light. That's a solid source quantum light. That's or in other words, we call a single photon emission. So each of those Murray structure that you see patterns here. So each of those patterns here, those are called Murray patterns. So here, actually, your excitons are trapped here. Okay, since they are trapped, and at some point of time they will recombine and there will be light. So that is just one photon. We call a single photon, and a single photons will be generated from here, everywhere. And this is just a structure, but actually in a real structure you will have millions of these. And we have the coherent emission of single photons. And those single photons are going to be used for quantum computing. So that's where we are heading. So, but for us, it is a solid state single photon source that we initially will create. And not only to create the structures, we will have the tool to measure the single photons. So that's also we are building.
So I know with like current chip making, they stack like 170 plus layers of materials on each other that build all these complex lattice structures and everything else. I guess I have two questions. One, to make this be useful, do you need to stack a bunch of these things on top of each other? And two, how many layers have you guys stacked of these different materials, just out of curiosity?
Oh, great. So far only 3 layers.
Okay.
Yeah. So actually, we have done only 2 layers, but some other they have done 3 layers. Because as soon as you are, so you can create untwisted many layers. Okay, you can go to 100 layers and still see some different properties. But as soon as twisting comes, you cannot just do what reference to what. So that is also important. You can have 2 layers. Let's say 2 layers exactly 0 degree rotation. The third layer will be, let's say, 1 degree with respect to the first 2 layers. Or the top 2 layers, twisted with respect to just bottom one layer. So, so that is more complicated. So we're just playing with 2 layers now. And this is one source of single photon emission, and we have other sources like boron nitride. We don't need it because there can be naturally boron defects or nitrogen vacancies, boron vacancy, nitrogen vacancies, or any other, carbon can come in and sit in the boron place or nitrogen place. So those are actually defects, and they can emit single photon. So our also focus is to look at those single photon from these materials. And in a large scale.
We're all for beer.
Yes. Thank you very much. So, to keep up with our tradition, we're gonna take our